Then the final part of today's revision lecture is the design patterns. So there were 9 design patterns that we covered, starting with the singleton pattern. So the singleton pattern is basically a pattern where you have objects where you only have ever one instance. Sometimes this is a dangerous thing to do. If they don't have a state that changes, it's fine. But you're effectively creating something that is a global variable. It is, and what is the problem with global variables? If they are variable rather than constant, they can be changed from anywhere in your program. If you change state anywhere in your program to any place where it uses this value, suddenly changes as well. So it becomes very easy to change state in an unpredictable way, and it becomes very hard to deal with this. But there are cases where singleton patterns come in. In particular, I say, okay, I want to cache some values. I need to have something to load these values. Okay, do I already have a connection to this database? Okay, then return the existing connection. Otherwise, I return create a new thing, and I keep track of the fact that I have this connection. In that case, you're using the state more as a cache, as a temporary memory to optimize stuff, rather than to actually change your behavior. In those cases, it can be a perfectly valid thing to do. Singleton pattern, and in Kotlin you can use the object, an object to implement this. You can also do it by hand, obviously, and it looks like this. So you create an instance inside it with inside a companion. It has a private constructor, so no one can create it. If you want to use it, you just need to get the instance out of the object, etc. Of course, a companion object is also a singleton itself, but let's not go there. So this is how you could implement that, and you can get the next number. Of course, if you now rely on the value of that next number, you're going to be struggling with, oh, is there something else now that calls this? Or you can even depend on the way that the JVM, the order in which the JVM initializes your classes might, if your class loading or constructor calls a get next number, then you're going to be dependent on the order in which that happens, and you really don't want to have that in your. The observer pattern. So the observer pattern is a pattern that basically allows you to register events. So you can attach yourself to something that can be observed, and when the observable changes, it will notify the observers in particular. So an example of here is the notify function that does this, that for each observer calls the update function. So you have an interface. What does an observer need to look like? And then you can have an implementation of such an observer that, let's say, prints updated once it's there, and this is how you use that. The iterator pattern is the pattern of allowing you to get every element in a container or a data structure of some sort, and it will just get through all of them. You don't care about how it works underwater, how you get those elements. It will just give you a range of elements. By the way, there's more than one ways of doing iterators. If you look at C++, they use iterators in a very different way, where they have a begin and an end one, and you say, okay, you're at the end of the iterator if you're at the end. And it allows some interesting concepts that Java iterators do not. In particular, you can use iterators to point to a particular location where you found an element. Java doesn't do that. Composite pattern is where you have a type that contains a container that contains children of its own parent type. So a composable interface might have a composite type that has a list of composables, and itself is also composable, and then you can do something for each of those. And when you need to do something for the composite, it will do it for each of the children. Example of this is, for example, the view group in Android, where you can, when you call the onDraw, or when the view group is drawn, it will draw all its children. When it lays itself out, it lays out all its children first, and then it lays it out itself. So you can compose in that way. Builder pattern is a way of handling the creation of complex objects that have some sort of data structure issue. So that may not be easy to create through a constructor. A builder allows you to do that. It might also be able to say, okay, you have an immutable instance, but the builder has mutable arguments and you can set it up. And when you build it, it might do some checking and things. But in particular, it handles the case where you have error-prone things with functions with many arguments, or especially constructors with many arguments. And Kotlin makes this slightly less important because you can have named parameters. So if you have a number of the same parameters, if you don't have names, it becomes very easy to don't or not order them correctly. Lazy initialization. In some cases, it is a good optimization of not determining the value of a property immediately, but only when you're first using it. In other cases, it is actually necessary to do so. For example, in the case where you'd say, okay, if you have, you could have used lazy initialization in your assignment when you have lines and boxes. So the lines adjacent boxes needs a box. A box needs a neighboring line, and they refer to each other. So you cannot, when you construct your line, the boxes might not exist yet, because the box might just have asked to create that line, but it's not created itself yet. Or another box might have started to create that line. So if you actually calculate it lazily, the boxes exist, just the parameters don't exist. So there's many cases where you might want to lazily do something. You can do it by hand, as I show here. You can say, okay, we give it a temporary value, and in your getter then say, okay, if it's an invalid, if it's a temporary value, I'm now giving it the actual value. Of course, it would not be a literal, but would be something you calculate or retrieve somehow, and then we return that value. This is a very naive, simple implementation. If you look at the implementation of the lazy object in Kotlin, it is actually a bit more advanced, including safe in multi-threading context, which this pattern is not. So lazy initialization is a common thing to do. Factory pattern. Sometimes you don't want to create instances by hand, but you just want to give me an instance of this particular interface rather than create an instance of a particular class. In the assignment, you'd had the mutable mutable matrix or mutable sparse matrix functions that would create you those and initialize them correctly. So you cannot do that initialization in the constructor because constructors cannot be inline, and the initialization needs to be inline a little bit to make it work correctly. Therefore, we have a factory that does this. In Kotlin, you can even give that factory the same name as the class and make it work transparently. There's other reasons why you might want a factory. So the type can be actually hidden from your users. You have an empty list. You don't care about what is used to create it. Often it's used to also reuse an instance of an empty list, because an empty list is an empty list. Any empty list is the same. So you want to have something. If you want to create an interface of type result type, you can then say, okay, create the result type function that will actually give you the implementation. The implementation can be private to the file that provides the factory. In this case it's not, but it could be. And then when you use it, you just get an instance of a result type interface by calling the function. You don't get to decide the implementation. Factories are quite common. The adapter pattern is basically when you have one interface, an object with one interface, and you want to behave like another interface or fit into a certain API that needs a certain interface. In this case, we're adapting to strings, but if you use a recycler view, you can have an interface that adapts into a list of items. And this is another version, an extension upon that adapter that we discussed, where we actually also create an iterator for that string adapter. So if you have any string adapter, I can actually call the iterator factory function that creates me an iterator for those strings that happens to be a string adapter iterator that implements has next and next. And because the iterator function is an operator, Kotlin knows to use this if you use a for each. It says, okay, do I have an iterator? Is this iterable? No. Is there an iterator operator for this type? Yes, there is. And it will use this correctly here. And that's one of the tricks you can do with Kotlin. You can get for every element in that thing, do something. The visitor pattern allows you to basically, sometimes you want to do something for each element, maybe even have a visitor could have a return type. So you want to allow people to add functionality in relation to your type, but you cannot do something specifically. You can use the visitor pattern. So your type implements a visit function, and in that visit you invoke the visitor with the right data. In particular, interesting thing is your visitor can actually implement multiple functions depending on different types of data, and then the visited object can call the right one depending on the data it has. So this way you can do something with a complex data structure and use it. And it allows also for something called double dispatch, basically depending on both the type of the object that you're doing it on as well as of the data inside it, where normally you can only dispatch on the object that you're calling it on. And in Kotlin you can even create an extension method that hides away the visitor, that creates the visitor and makes this all work. So you can effectively, you can almost do polymorphism with extension methods using the visitor pattern.